Our next speaker is a professor with the Department of Electrical and Computer Engineering at the University of Victoria. She is an NSERC EWR Stacey Memorial Fellow, an Engineering Institute of Canada Fellow, and an IEEE Fellow. She has co-founded and chaired the IEEE Victoria Section Vehicular Technology and Communications Joint Societies chapter. She is an elected member of the IEEE Vehicular Technology Society Board of Governors. She is the Associate Editor-in-Chief for IEEE Transactions on Vehicular Technology and has served as a distinguished lecturer of the IEEE VTS Society and IEEE ComSoc Society. Ladies and gentlemen, let's welcome Professor Lin Cai.
Yeah, thank you. Thank you for the nice introduction, and thanks everybody for attending. My talk today is about reliable and scalable vehicle-to-everything for intelligent transportation system. Talk about the transportation system, let's see how it influences our civilization. Since our human walking upright use 2 legs, this is a major milestone for human civilization. Since then, we can see no great civilization has been built without some well-defined system of transportation. Let's take a look starting from the industrial revolutions in 19th century. We see a few milestones here. First is telegraph, which makes the transportation of information to sub-second level. One way to measure distance of humans, we are like intelligent peoples, is the round-trip delay to exchange information, because any intelligent thing needed to exchange information. And so telegraph shortened the distance of human beings. Second, we apply steam engine in rail transportation. It made the land transportation independent of human or animal muscles. Third, the steamship further sped up global transportation across continents, leading to the first era of globalization period. Industrial revolution in 20th century was first associated with the combustion engine and automobile, followed by modern highway systems. Airplane was invented in 1903, leading to a much faster way to transport people and goods. By the end of the last century, we have witnessed the largest man-made system, connecting more than half of human population globally. This is the internet. From the first industrial revolution, modern society is highly related to modern transportation, which completely changed the way people traveled and how goods were transported. Modern society depends on the ability to transport materials, goods, and people over long distance, much faster, safer, and at lower cost. Here are some statistics showing our dependence on transportation. Note that in the developed countries, the green parts here, the number of motor vehicles far exceeds half of human population. With the world population nowadays hit 7.9 billion and the ever-growing mobility needs, the transportation systems today, however, encounter greater challenges. First challenge is the safety challenge. Since 2007, there are around 1 million deaths per year due to transportation accidents, and this number keeps flat. This tops the cause of deaths for the age group between 15 to 29 years old. It also accounts for about 3% GDP loss for low or middle-income countries. Second challenge is mobility. On average, each US commuter wastes around 97 hours per year in traffic, and the annual loss due to urban congestion is about $160 billion. And the situation in Europe and in Asia are even worse. Third challenge is about environment. Transportation accounts for 29% of greenhouse gas emissions in US, one of the largest sources leading to environment challenges. Last, I'm not sure whether you notice it. When you purchase a car, it sits unused 95% of the time, demanding a large amount of parking spaces. The parking fee may exceed the cost to use the car in big cities. Today, autonomous and electrical vehicles are promising for future intelligent transportation system. It can help to enhance safety, reduce congestion, cut harmful emission with greener energy, and enabling car sharing to save space. So these can address the four challenges we mentioned just now. Countries worldwide are developing related policy and investing on infrastructure to prepare for autonomous vehicles. This figure shows autonomous vehicle readiness index. Singapore ranked the highest, followed by Netherlands, Norway, and the US here. However, autonomous vehicles also faces grand challenge. We can see in March 2018, Tesla has this fatal crash, make the driver killed. And in the middle, we can see the same month, Uber has a fatal accident, which make a pedestrian being killed. So follow this accident, Uber, NVIDIA, and the Arizona governor all announced they want to suspend the self-driving tests. And after that, we can see like Tesla's share price fell dramatically. So these accidents are major setback for autonomous driving. Another accident here happened in June 2020. Is a Tesla crashed to a truck in a highway. So these accidents tells us safety and reliability are grand challenges for autonomous driving. What leads to this grand challenge of autonomous driving? If we compare this standalone autonomous drive car with these professional drivers, we found that these professional drivers, they can see and hear each other with cues. On the other hand, autonomous vehicle needs lots of sensors, memory, learning, and decision-making functions. The sensors in autonomous vehicles have various limitations. For instance, radar is not capable to detect complex shape due to low resolution. LiDAR has high resolution, but it is short-ranged and weather-sensitive. We conclude it's better if a vehicle can talk. In other words, it is preferable to let a vehicle communicate with each other, with the infrastructure, with the sensor, and so on. Our objective is to overcome the limit of standalone autonomous vehicles, as each vehicle has a limited sensing range, and the amount of data acquired by a single vehicle is limited for AI algorithms. Therefore, we should let vehicles share sensed information and forming a network dynamically. With that, each vehicle can access long-range sensing information and can talk to each other in addition to its own observation. Then the driving decisions can be made faster, more reliable, and more accurate. The breakthrough towards the objective is vehicle-to-everything communication technology, V2X. V2X is the umbrella term, including vehicle-to-vehicle, vehicle-to-infrastructure, vehicle-to-pedestrian, vehicle-to-cloud, vehicle-to-sensor, everything. Let's take a look at a few V2X applications. Using vehicle-to-vehicle communications, vehicles can exchange warning messages to avoid collision due to blind spot, lane change, left turn, etc. Similarly, vehicle-to-pedestrian can exchange collision avoidance message using vehicle-to-pedestrian communication. And then by exchanging information between vehicle and infrastructure, traffic lights and street light control and management can be more intelligent. And we can even let intersection movement be assisted by this V2X to help drivers avoid or mitigate vehicle collisions at intersections. And by real-time message exchange between vehicle and clouds, Numerous new business models and revenue streams can be created. For instance, smart parking, fuel management, including electric vehicle charging management, location-related advertisement, insurance, etc. Last but not least, V2X can assist automated transportation, help to form, say, vehicle platooning, let vehicle share sensing information, assist semi to full automated driving, and even remote controlled driving. According to market estimation, globally, connected car market size may reach $212 billion by 2027, from an estimated value of $42.6 billion in 2019, at a 22.3 annual growth rate. So this rate is quite high. Imagine if we can deposit $1 today in a bank with such a growth rate, interest rate, then this $1 will become $1,000 in 35 years. So this growth rate is super high. Meanwhile, as researchers and engineers, V2X communication systems do present us tremendous technical challenges, which are also our research opportunities. First, high mobility of vehicle deteriorates channel conditions and data rate. Then, frequent changes of topology due to mobility affect network performance. In addition, for intelligent transportation system, integrity of data is crucial. If the transmission has low reliability, chain accidents may occur. Finally, heterogeneous vehicles will share the same road. Heterogeneous devices and applications will present different connectivity and quality of service requirements, which are difficult to support. Let's take a look on the major challenge for V2X. Vehicle networks aim to support many new applications, ranging from time-critical safety message exchange to delay-tolerant data dissemination. A large percentage of data may need to be broadcast or multicast in a highly dynamic network. Their service requirements are quite different from traditional internet applications. We know for traditional internet application, the network needs to deliver data to a particular user with a given IP address, no matter where it is located. And the internet application quality of service are typically measured by, say, throughput, delay, loss, jitter. In other words, internet applications care about who, identified by the IP address, and when. Safety message in vehicle network should be broadcast to all vehicles in an area before certain location-dependent deadline, no matter who is at that location. So we don't care about who and when. Here we care about where and when. In our JSEC 2011 paper, we define the time and the location critical reliability for vehicle communication services. Here, the coupled time and the location criticality is the key. This is an open issue to address. In addition to this time location critical reliability, vehicle density can change fast over time and space during rush hour or in a highway. So in some situations, there may be thousands of vehicles per square kilometer. This is the place where V2X is most needed, while the V2X communication systems using today's technology may be too congested to be functional. So scalability is a great challenge. The reliability and scalability challenge of connected vehicles have attracted extensive research. In the following, I will brief the technologies, mainly from the media access control layer and the resource allocation part. Let's take a look. The first important standard for V2V communication is the DSRC, Dedicated Short-Range Communication. Its MAC protocol is defined in IEEE 802.11p standard. IEEE 802.11p is formed in 2004 based on CSMA Carrier Sense Multiple Access, which is similar to our Wi-Fi MAC. Each device needs to sense the channel before transmission to avoid collisions. However, CSMA encounters a serious issue in a large-scale network. This is about hidden terminal. So let's take a look of this example. This green car and this blue car are somehow far away from each other and cannot sense each other. So when for instance, when the green car wants to transmit, cannot sense the blue car. So two of them can transmit simultaneously at the same frequency and time. And then their transmitted packets will be collided here. So this red truck cannot hear neither the green car or the blue car, nor the blue car. So high collision probability will be happen due to this hidden terminal issue. And high collision probability will lead to low reliability and efficiency. In addition, in V2X, an important application is beacon broadcasting, where vehicles need to broadcast their location, speed, acceleration to nearby vehicles periodically. However, for broadcast or multicast transmission, it's harder to implement a feedback mechanism. So 802.11p didn't adopt any feedback mechanism for this beacon broadcasting. So the sender has no knowledge whether a transmission is failed or not. So without feedback, what they can do is the sender can do this blind retransmission, which means it transmit the same message again and again. But we can see this blind retransmission will lead to low efficiency and also will introduce more collisions. So this is the issue. Another standard, in 2014, 3GPP LTE release 14, standard release 14 defines its CV2X standard. This is about 10 years after DSRC 802.11p. So this 3GPP LTE CV2X reuses many DSRC CITS established technologies, mainly in the upper layers, including application layers, security and transport layer, etc. And this CV2X standard focuses on enhancing the bottom physical layer and the link MAC layers to support V2X use cases. 3GPP defines two complementary communication modes. In the left-hand side is the PC5 mode, where vehicle and vehicle can directly communicate with each other using the ITS band, which is cheaper than the cellular band. The other is UU mode, similar to the existing cellular system. The vehicles can communicate with the base station, use traditional mobile broadband spectrum. In this talk, we focus on this PC5 mode. Here, the vehicle can directly communicate with each other without the involvement of base station, and it can use the ITS band. To better support vehicle-to-vehicle in CV2X physical layer, considering this vehicle in opposite direction in highway will have a relative speed of several hundred kilometers per hour. And this ITS band has high frequency at 5.9 gigahertz. So in the physical layer, the CV2X in standard introduced this demodulation reference signal, DMRS, in order to handle this high Doppler frequency shift. Okay. And then in the MAC layer, media access control layer, the wireless resources, the spectrum band is divided by subchannels. Okay, the frequency is divided to subchannels. And each subchannel consists of a side link, control information, SCI, followed by a transport block transmission part. So this green part is used to deliver data, and this red part is SCI. And the SCI includes selection counters and the many information such as the modulation and the coding schemes that will be used in this current transmission, and also includes some making important information like risk selection counter tell others when the vehicle is going to release the occupied resource and perform risk selection procedure. Let's give another example to talk about this selection issue. So in CV2X, this new MAC protocol is called SPS semi-persistent scheduling. This is particularly helpful for those applications such as beacon broadcasting, because beacon broadcasting traffic is quite periodic. So this SPS let vehicles to try to stick on the same resource periodically. Okay. So this SPS essentially is still a sensing-oriented access scheme. Specifically, like the vehicle traffic, as we mentioned, is periodic. Then the time domain, we also divide the time into periods. Okay, so in CV2X, when a vehicle just comes and want to choose a resource or choose a subband to transmit, the vehicle needed to take a look of what's going on in the channel for a while. Okay, so in this whole period, so this red or brown part are the resources which has already been used by other ongoing transmissions, and these green ones are the available resources. So this vehicle will randomly select one of these available green resources and start to transmit its own SCI and packet. Once the first packet is transmitted successfully, it is equivalent to make a distributed reservation for the resource used, because other vehicles will avoid them when other vehicle need to choose the resource to use. And once one particular resource is chosen by this vehicle, the vehicle will set a counter and make sure like the same resource will be keeps on use for a number of times until the counter going back to 0. Given this SPS in CV2X, we first try to develop an analytical model to quantify its performance. And here is the simulation and analysis results. The x-axis is the vehicle density, and the y-axis is the access collision ratio. We found that when the vehicle density becomes high and the access collision ratio is quite high, so looks like the SPS didn't well address this reliability issue. Okay, so we found that this is because SPS didn't solve this hidden terminal problem. When two vehicles are hidden terminal to each other, they may select and thus reserve the same resource for transmission. Even worse, as both vehicles will stick on the same resource for a number of times, we call it RC counters, reselection counter times. Okay, then which means once the collision happens, it will happen RC times rather than like random select another one. So SPS didn't well address this hidden terminal, and then the high collision and the low reliability is still the situation. And the second issue is the scalability. SPS didn't well address the scalability issue either. It cannot handle the situation of congested network with thousands of vehicles per square kilometer. Finally, due to lack of feedback for broadcasting, beacon broadcasting, SPS still has to rely on blind retransmission similar to 802.11p case. So this will lead to more collisions and low efficiency. So given these impairments, next we investigate whether or not we need to care about these communication impairments. Or let's see how severe these communication impairments will affect effective vehicle control applications. So we focus on this important application, platooning. Platooning is one of the most important applications for connected vehicles. When vehicles can sense and exchange status information with each other, ideally, in the ideal case, all vehicles in the same lane can construct a platoon. So vehicles in the same lane can move at almost the same speed with very short distance between them. So platooning is very promising to increase road efficiency and avoid transportation congestion, also enhance energy efficiency and safety. And in this left figure, we show the communication message exchange among vehicles using SPS. And the right figure shows the control aspect of platoon vehicles. Given the received message from each other, how each vehicle can change its status by accelerating or braking, so the platoon formation can be maintained. Okay. However, if we consider like the communication impairments, we found that the communication delay and the reliability has a huge impact on platooning. Here in these two figures, we consider a vehicle which is a header followed by 12 other followers. And the header vehicle will move in a constant speed, which is showing this yellow curve, 10 meters per second. And the 12 other followers try to follow it, which means try to maintain their speed to be as close to 10 meters per second as possible. And the right figure shows if the communication delay bound is 20 milliseconds. In other words, the beacon message of each other can reach its neighborhood within 20 milliseconds. Then we can see the reliability is relatively, the delay is tight and the reliability is high. Then in this case, all vehicles can maintain almost similar velocity close to 10 meters per second. Okay. However, if the delay becomes higher because sometimes the transmission is in error and we need to retransmit the packet so on so forth. So the communication delay becomes looser and looser up to 200 milliseconds. So in this case, we found we have the same header, but the follower, the speed will oscillate greatly above or below 10 meters per second, which means in order to make these platoon vehicles safe, we need to enlarge the gap between vehicles, and the vehicle platoon formation is not stable in this case. So these two figures shows us the importance of reliability and a delay for vehicle platoon control. So how possible we can guarantee the communication be super reliable and within short delay instead of the long delay case. So this is our key objective. So the first issue to address this timely, high reliable transmission is how can we minimize these collisions due to hidden terminal? And we notice that SPS has suffered severe reservation collisions due to hidden terminal. So we come up with a distributed reservation media access control to address the issue. We use coded preamble to avoid collision due to hidden terminal and provide feedback to resolve collisions. And we also come up with adaptive power control to mitigate congestions. Here is a simple example. In the existing system, when a new vehicle wants to access the channel, it will first listen. And in this case, this new car finds that the blue car is not in use, so it decides to use the blue channel is not in use, so it decides to use the blue channel. However, the hidden terminal here, this car has already used this blue channel. Then these two cars broadcast beacon message will collide again and again. Okay, to avoid that, this is our solution. When the new vehicle senses the channel and try to use the blue channel, before it directly use that, it needed to send in some control information to its neighbor to see, can I use blue channel? Then if this middle car here notice there's already someone used the blue channels, and it will notify this new vehicle, no, it cannot be used. So in this case, the vehicle can choose some different channel to use to avoid the collision. So the coded preamble is used to help this control information exchange, mainly to notify reservation collision, beacon collision. It is assumed that once a resource unit is reserved successfully by a vehicle for beaconing, it will not be released until the vehicle leaves the system or collision happens due to topology change. In order to define some orthogonal preambles, we just reuse the 64 orthogonal preambles in LTE system, and we just redefine them to give them different meaning. So the 64 preambles in LTE has been redefined into fulfill a few different functions, such as collision detection, facilitate access the channel, and etc. In our distributed and adaptive reservation MAC protocol proposed, we have 4 types of preamble. Preamble R for regular transmission, preamble D for data transmission, and the preamble DT for declining collision detection, and the preamble T for transmission stop notification. And let's take a quick look of 2 simple examples. So in the example in figure left, the new vehicle first choose resource 1, but this resource 1 has already been used by this vehicle 1. So in this case, vehicle 2 will notice this collision, will notify new vehicle resource 1 cannot be used, and then the new vehicle can choose another resource to use. And in wireless communication, we know the channel is not always reliable. In this case, for instance, the preamble D used by vehicle 2 to notify new vehicle is lost during the transmission. In this case, the new vehicle and some existing hidden terminal will use the same resource to transmit, and a packet collision can happen. In this case, the vehicle 2 can detect that packet collision and use preamble T to notify these 2 vehicles to choose some other resources. And the simulation use NS3 driven by Sumo traces show that in a city environment with light traffic, the proposed distributed reservation protocol can reduce the beacon loss ratio by almost 2 magnitude. And if in a city with heavy traffic, then both proposed protocol and the existing 802.11p need to add this new adaptive power control to reduce their collision probability. So compare these 2 with power control, we found that the proposed one can also cut the collision by 90%. The second problem is when there is packet loss due to channel impairments, how can we effectively recover those lost packet quickly? We propose a collaborative retransmission solution using network coding. When a vehicle accesses the channel, it can transmit a preamble plus 2 transmission opportunity to transmit 2 packets. And the first transmission opportunity will be used to transmit its own beacon, and the second transmission opportunity will be saved to help other lost beacon. So in addition, these preambles are the orthogonal sequence for collision resolution and the negative acknowledgement. This part is similar to what we have introduced for this distributed reservation MAC. Okay, and we also include this negative acknowledgement mechanism for feedback. So when a vehicle fails to receive an original beacon message, it can broadcast a negative acknowledgement. So let's take a look of a simple example to see how it works. Here, these 5 vehicles will broadcast their beacon sequentially. Vehicle 1's beacon message is successfully received by vehicle 345, but lost here at vehicle 2. Then vehicle 2 will immediately send a negative acknowledgement to let everybody know. And the next, vehicle 2 takes a turn to broadcast its beacon message. In this case, the vehicle 2's message is received by vehicle 134, but lost at vehicle number 5 here. So number 5 will send a negative acknowledgement. Next, vehicle 3 takes the turn to transmit. Okay, so using these 2 transmission opportunity, the first transmission opportunity, vehicle 3 still broadcasts its own beacon message, And the second transmission opportunity, vehicle 3 noticed there are 2 negative eggs for the message from vehicle 1 and 2, and vehicle 3 has received both successfully. So in this case, vehicle 3 can use a linear combination with network coding to transmit this linear combination of beacon 1 and beacon 2 simultaneously within this transmission opportunity. And in this case, vehicle 5 can use this retransmission to recover its lost beacon from vehicle 2, and the vehicle number 2 can use this retransmission to recover the beacon from vehicle number 1. Okay, so in this case, we can see that using network coding, we can effectively recover lost message by this collaboration between vehicles in the neighborhood. Here is some simulation results. We notice that from the simulation results, the proposed network-based based loss recovery method, so these blue and green bars, it can help to reduce the beacon loss ratio by 65 to 90%. Okay, so original loss ratio is this much, and using our solution, we can reduce that. And in addition, we found that 90% of the recovery can be done within 30 to 65 milliseconds. And we address this collision problem, we address this packet loss recovering problem. And then the next fundamental question is collision always equal to packet loss? The answer is no. In recent years, we have seen NOMA, non-orthogonal multiple access, has been an active research topic. And the successive interference cancellation, SIC, has been proposed to implement this NOMA solution. When two transmitters transmit in the same time frequency, we can decode the high energy signal first. So for instance, if this blue and the red signal mixed together, because this blue one has much higher energy, we can treat the red one as a noise and decode this blue one first. And then after decode this blue one successfully, we can remove this by interference cancellation technology, remove these blue ones, then we can decode the red one. Okay. So in this case, using SIC NOMA, we can achieve much higher efficiency than TDMA or FDMA. However, this is only possible if one signal is much stronger than the other one. There is a bigger power gap between them. So if we have the situation two signals mixed together have similar power, then this SIC does not work. So this SIC have a very somehow limited application in practice, particularly in the situation the power control is difficult or the channel is so dynamic we cannot control the received signal always have this power gap. So we have this follow-up question: is it possible to develop a new NOMA technology that can decode the superimposed signals without worrying about their power gap? So our team has achieved this innovation. Let's observe the superimposed signals when two signals transmit simultaneously. Okay, then each signal can be viewed as a vector. In the receiver side, the two signals are decayed or amplified by the channel and antennas, and their phase may be shifted due to the propagation delays, etc. So nevertheless, the two superimposed signals at the receiver end can still be viewed as the summation of two vectors, and then this is still a vector. Then if we can estimate the channel, the delay, theoretically we can decode the two superimposed signals. For this example, the two sender transmit two BPSK signals. If we ignore the noise, then in the receiver side, from this constellation we see if both users send bit 1, we should have received the constellation here. If user 1 transmit bit 0 and user 2 transmit bit 1, then we should receive something here. On the other hand, if we receive something here, we know sender 1 transmit bit 0 and sender 2 transmit bit 1. So intuitively we can decode it. Although the idea is very intuitive, but there is no practical system implement this idea. When we try to build a prototype to implement it, we did encounter tremendous technical challenges. First of all, the synchronization between 2 transmitters and 1 receiver. This is very difficult. Due to hardware limitation, we know there is no 2 devices have exactly the same oscillation frequency. As a result, when 2 senders and the receivers transmit, do the thing, we will find that the 2 sender and the receiver have different carrier frequency offset, Zangpo frequency offset, Zangpo time offset. So all these offsets are trouble. So all these offsets will complicate the receive the constellation, make this constellation more and more difficult to decode. Second, when 2 signals are superimposed at the receiver, given all these offsets, it becomes impossible to control the phase difference of these 2 signals. So, which means in some special situations, for example here, the received 2 signals from user 1, sender 1, and sender 2 has a phase difference of 0. Then we will see this situation when both of them transmit bit 1 and both of them transmit bit 0, we can see these 2 constellations are far away from the rest. But when user 1 transmits 0, the other one transmits 1, or 1 0 case, 0 1 and 1 0 case, these two situations will have similar received vector. Then in the other case, if we receive something here, we don't know whether this is due to 0 1 or 1 0. This make our decoder very, very difficult, or it will introduce extremely high error rates in this situation. And in addition, like in vehicle network, we have mobility, which will introduce fast fading shadowing. And for wireless communication, we have limited spectrum, so efficiency, cost constraints, these are all big issues. So our team tried to address this challenge step by step. First, we address the CFO, SFO, STO issues and implement our solution use the USRP platform. In our proof of concept test, 2 senders are carried by 2 vehicles in the front and in the end, and the middle vehicle carry the receiver. And we use GPS clocks for time synchronization. Our experiments was conducted on both the residential area with a low speed and on a road with high speed. From the bit error rate results, we prove our concept that our proposed solution can effectively handle CFO, SFO, STO, all these offsets, and decode the superimposed signal successfully. If you are interested, you can take a look of our TWC paper. And the next, due to hardware limit, we cannot control the phase difference. We mentioned this challenge. We will encounter this 0, 1, 1, 0 undistinguishable situation. We try several methods to address this issue. First, we try to use simple repetitive code with some phase maneuver to reduce the bit error rate due to indistinguishable signals. However, using repetitive code reduce the spectrum efficiency, which is not desirable. Finally, we design a new weighted rotation code, which can effectively reduce bit error rate while maintaining the transmission efficiency. The detailed design can be referred to our recent publication in Journal of IoT. And the experiments results show that no matter whether 2 superimposed signals have similar or different power levels, our NORMA solution can effectively decode the signals with low BER, and more importantly, we can maintain spectrum efficiency, that the transmission time to send 2 signals by 2 sender is reduced by half compared to TDMA. So in summary, in this talk, we first analyze the performance of existing MAC protocols used in V2X by quantifying the collision probability and the delay distribution. We also analyze the impact of communication impairments on platooning control The results show how to ensure high reliability within a short time period is very important. To address these challenges, we first propose distributed and adaptive reservation protocol to minimize collision probability. We then design a network coding-based group retransmission solution to recover transmission errors. And then we propose a new NORMA solution that can decode the superimposed signal no matter whether the signal have power gap or not. So with reliable and scalable V2X technology, we imagine future connected autonomous vehicles will become cloud-controlled mobile robots to deliver materials, goods, and people to the precise location at a given time precisely. This will reduce transportation storage costs and delay, improve road and energy efficiency, and improve vehicle utilization. Down the road, combine V2X technologies with edge cloud computing. This can enable numerous new applications that beyond what we can imagine today. They will not only revolutionize how things and people are transported, but also likely how information and energy are exchanged and delivered. They will sit in the center stage for the next industry revolution. With that, we thank you for your attention. Now I'm happy to take any questions or comments.
Thank you so much, Professor Lin Cai, for that comprehensive presentation. And now, of course, we'll move on to the Q&A, starting with this question that we have from our audience. And it's, what are the main challenges for medium access control in vehicular communication systems compared to other wireless systems? What are the main challenges?
Yeah, this is a good question. It's quite important for our research direction because traditionally, like our Wi-Fi system, the wireless communication system mainly supports human-to-human communication. Like we want to access the internet, web browsing, we want to exchange like audio, video contact between humans. And humans are more intelligent than typical machines, which means a human can tolerate some errors and can tolerate certain level of latencies. So when we move to vehicle communications, this message exchange is important for the safety of the transportation systems. And any message loss or a severe delay, etc., will introduce potential like hazard to the transportation systems. So this delay requirement and the reliability requirement in V2V is much more stringent than the typical human-to-human communication systems. So this is one big challenge. The second big challenge is in V2V, usually like the types of transmission is from a single vehicle to all the neighborhood vehicles. So this is no longer a point-to-point communication system. We need to consider point-to-multi-point, or sometimes multi-point-to-point, or sometimes multi-point-to-multi-point kind of communication mode. So the communication mode in V2X is quite different from the traditional wireless system. And we can understand all these multicast or group casts. They have tremendously different like features and structures compared to point-to-point unicast applications. So it's important to leverage that when we design the MAC protocol, considering these traffic features and service modes. And I've already mentioned the scalability and heterogeneity is also an important issue, like different from, say, Wi-Fi system or cellular system, the devices are relatively homogeneous. In vehicle transportation system, we have all kinds of vehicles, big, small truck, or single, or even sometimes a cycle pedestrian need to share the same road. So they carry different types of devices, and these devices need to exchange information timely. So all these are important issues that need to be considered when we design our MAC protocol.
Thank you so much for that deep dive, Professor, into that question. We have a few more questions to go over here. Thank you so much to the audience for the participation as well. And this is the next question. You proposed a new NOMA, I'm not sure I'm pronouncing this correctly, and NOMA is
Yeah,
spelled
yes,
NOMA, technology
right.
without power control. Why do you think without power control is an appealing feature?
Yeah, because like the traditional like SIC, it can achieve this network channel capacity only if the two signals have very huge power gap. And in many situations, for particularly for Internet IoT, Internet of Things, like there is no closed loop power control available to maintain these types of power gap. And furthermore, like in vehicle communication systems, due to high mobility, and the environment, the channel environment is highly dynamic. So when you imagine the channel fading ups and down quickly, so even though you have some gap at the beginning due to this highly dynamic channel, so in the end at the receiver side, so these two received signal may still have similar power. So when you have this similar power, then this SIC does not work, so which limit the application of NORMA. And then in our systems, we don't need to worry about this kind of, we have some results shown here. Yeah, in this experiment, we have two users, two sender, Alice and Bob. In this experiment, two sender maintain certain about 2 dB gap of their transmission power. And in another set of experiment, this we change its power gap. Sometimes they will have exactly the same power, so on and so forth. We found that no matter we maintain a power gap or there is no power gap, our solution can still decode the two signals successfully with high reliability. So, which means our solution is much simpler to has a much wider applications and simpler to implement without the need to have maintain this kind of strict power control. So I hope I answered your question.
Yes, thank you so much for those perspectives that you shared with the audience. We have another question here, and it's what are the important future research issues for vehicular communication systems? Your thoughts, Professor?
Okay, yeah. I've already mentioned a few of the future importance direction for vehicle communications, and I should add a few more because, like, in addition to scalability and reliability, because this vehicle communication system is related to the safety, public safety, and we found that these types of application also require high security and trustedness. Imagine if in a high dense highway system, every vehicle rely on V2V communication to do the control of its speed, etc. If some malicious users come and broadcast some untruthful messages, and this will introduce significant safety issues to the transportation system. This is something we need to definitely avoid. So I think one important issue in the future is we can leverage all types of information, the information exchange between vehicles, as well as the existing sensors in the vehicles, as well as not only wireless communication, but we can also leverage other types of visible light signals, so on and so forth. So with all these different types of information sources, we can somehow fuse the information together and understand which message is trustable or has high security level, and what types of messages is suspicious, and we need to pay attention to that. And if there is certain things suspicious, we need to remove them from the system and have a warning signals to all the audience, all the other like vehicles, so on and so forth. So I think in future vehicle communication system, how to maintain high dependability, how to high trustworthiness, and high security, etc. These are all very important research issues.
Definitely, indeed. And of course, that last answer, Prof, helps us set up the next question, which is related to the last one. And it's this: how can signal hacking be prevented? Do you have a solution?
Yeah, very good question. Yeah, I have this in my mind for a while because like we know like technology can be like a double-bladed sword. So if we apply it correctly, it can help us. But if some malicious users apply it, it will hurt us. I think in current wireless communication system or networking system, we have seen all kinds of security and security like solutions to enhance the security level of communication. But in vehicle communication system, because of our new feature, we are communicating with strangers all the time, so on and so forth. Then this security concern becomes even higher. But on the other hand, like we can think about in our daily life, what can we deal with all kinds of suspicious actions? So we will use multiple sense information to make decisions. Similarly, in our vehicle network, if some vehicles report some wrong message, say if I broadcast a message, I'm currently speed up while I'm slowing down, then because the wireless signals have certain propagation features, they will not lie. So at the receiver side, I can use this, for instance, measure the Doppler shift or measure the phase change, etc., can sense whether this vehicle sending this information report I am accelerating is truly accelerate or not. So that's what I mentioned just now. We can not only receive the message and decode the data, but also receive the message and signal process that message. And through this signal processing, we can find whether the data it transmitted and the observation from the signal processing match with each other. Then this will substantially enhance the system security level without the costly, say, encryption, decryption types of solution. So this is one of the vision I have. I think this will be a promising direction. So in addition to decode the data, we need to signal processing the sensed, received the bits.
Wonderful.
Yeah, I hope.
Now let's spend the last 3 minutes of this session to answer this final question we have here. And it's,
Sure.
Is the research output applicable for vehicle-to-vehicle comms or vehicle-to-future 6G edge computing brackets centralized control? Is it?
Yeah. Can I say the question again? Can I hear the question again?
Sure. The question is the research output applicable for vehicle-to-vehicle comms or vehicle-to-future 6G edge computing, and then in brackets it says centralized control?
Okay, yeah.
That's the question.
Of course, here in today's talk, we focus on V2V communication without the involvement of a base station or roadside unit. Definitely, many of the research output here are applicable for vehicle to infrastructure and vehicle to base station. For instance, for example, here, like we can still use this kind of normal solution in this V2 infrastructure or V2 base station communication to further improve the spectrum efficiency. So although our system model or the starting point is V2V, many of the technologies we introduced here is applicable to V2I or vehicle to base station. In 6G, we can still think like these two communication mode will coexist. Even in 6G, we does not necessarily everything needed to go through the base station. Because due to the physical limits, like if two vehicles are next to each other, but your message needs to go to the base station and coming back, or go to a roadside unit and come back, the propagation delay will be enlarged, so on and so forth. So I think in 6G, this V2V and the V2I will still coexist. I hope this answers the question.
Thank you so much, Professor Lin Cai, for helping to answer all the questions from our audience, and of course for that in-depth look at reliable and scalable vehicle to everything. Thank you so much.